Welcome back, everybody, for another deep dive. And today we're looking at something pretty interesting, a math puzzle that's over a century old.
Oh, wow.
Can you dissect an equilateral triangle into pieces that then you can rearrange to make a perfect square? So it sounds kind of simple, but mathematicians have really been kind of struggling with, like, what's the minimum number of pieces that you need to do this?
Right. Yeah, it's not just a theoretical exercise either. These
Right.
these dissections have real applications, especially when you're working with thin materials.
Yeah.
Like imagine optimizing fabric layouts in clothing manufacturing.
Oh, interesting. No. Okay.
Yeah.
Let's set the stage. Back in 1907, Henry Ernest Dudeney, an English mathematician, he cracked this puzzle with a four-piece solution.
Wow.
It's over 120 years ago. Pretty impressive.
Wow.
But the question has always been, like, could it be done with fewer pieces? Could it be done with three?
And that question has lingered until just recently.
Oh, really?
A team from JI's and MIT has finally definitively proven that Dudeney's four-piece solution is the most efficient possible.
Wow, that's huge.
There is no three-piece solution.
A century-old debate settled.
Mm-hmm.
But hold on, help me wrap my head around this. Why can't you just do it with two pieces, it seems like?
Yeah.
You know, with the right cuts, any two pieces with the same total area should work.
That's where the geometry gets interesting.
Okay.
You're going to think about the perimeter. An equilateral triangle has three equal sides to form a square. You need four equal sides. No matter how you slice a triangle into two pieces, you can't create those four equal sides from the original three.
I see. So two pieces out just based on just what the shapes are.
Right.
Okay, that makes sense. But three pieces, that seems like a much tougher nut to crack.
Absolutely.
Yeah.
To prove that there's no three-piece solution, they had to explore all the possible ways to dissect a triangle into three pieces.
Right.
And then show that none of those combinations could be rearranged into a square.
So how did they do that? Did they just sit there trying every single permutation that sounds exhausting?
It would have been incredibly time-consuming. But luckily, they developed a clever tool called a matching diagram.
Oh.
And this creates a visual language to represent the relationships between the sides and corners of the triangle and the square.
Okay, slow down for me. How does this visual language work? Give me an example.
Sure. So imagine you have a triangle that's divided into three pieces. Each piece has sides and corners, right?
Right.
Now you picture a square also divided into three pieces.
Yeah.
The matching diagram lets you compare the length of each corresponding side and the angles at each corresponding corner between the triangle pieces and the square pieces.
Okay, so you're making like a blueprint
Yeah,
of the relationships between the two shapes.
exactly.
But how does that prove that a three-piece solution is impossible?
Because if you can't create a matching diagram where all the corresponding sides and angles are equal, then, those three triangle pieces can't be rearranged to form those three square pieces. They just won't fit.
So they went through all the potential three-piece triangle dissections
Okay.
and showed that none of them could create this valid matching diagram with a square. And that's how they definitively proved that Dudeney's four-piece solution was the best.
Exactly.
That's so elegant but kind of mind-bending.
It is. And what's really neat is that this matching diagram technique isn't limited to just the triangle square problem.
Oh, really?
It can be applied to all sorts of other dissection puzzles.
So this isn't just a solution to one old puzzle. This is like a tool to crack a bunch more.
Exactly.
Okay, we've laid the groundwork. I'm dying to dig deeper into this proof. Let's get into the nitty-gritty in the next part. Okay, so let's pick up where we left off. We were just starting to unpack the details of this proof.
Right. So let's imagine a specific three-piece dissection.
That's right.
Like, let's say you cut the triangle into two smaller triangles and one quadrilateral.
Okay.
So to prove that this won't work, we need to show that no matter how you arrange those pieces, their sides and corners just won't match up perfectly with any possible three-piece dissection of a square.
Okay, I'm visualizing it, but that seems like you'd have to check like an infinite number of configurations.
Yeah.
How could they possibly be sure they covered everything?
Well, that's the beauty of the matching diagram.
Okay.
It gives you a way to analyze the relationships without having to physically manipulate the pieces.
Right.
Remember, it's all about those corresponding sides and angles.
Okay, so walk me through. We have our two triangles and a quadrilateral.
Right.
What would we look for in the matching diagram to prove that it can't form a square?
So let's focus on the corners, like the vertices.
Okay.
So in a square, every corner is a right angle, a 90-degree angle.
Right.
But in our triangle dissection, we have a mix of angles. Some might be right angles, but others are going to be 60 degrees because we started with an equilateral triangle.
Ah, I see where you're going with this. So if our matching diagram shows that we can't line up enough right angles from the triangle pieces to make the four right angles we need for the square,
Yeah.
then we know it's not going to work.
Exactly. And
Right.
the same logic applies to the sides, too. A square has 4 equal sides, but our triangle pieces are going to have all sorts of different side lengths.
Right.
A matching diagram would tell us if we have enough matching side lengths to form the square's perimeter.
So they basically went through all the possible combinations of these angles and side lengths
Right.
and showed that no matter how you cut up the triangle, those 3 pieces just can't be rearranged to make a square.
Precisely. They systematically eliminated every possibility.
Wow.
Which is why this proof is so significant. It doesn't just give us a solution.
Right.
It definitively proves the optimal solution. It closes the door on over 100 years of speculation.
I'm really starting to understand the power of this matching diagram.
Yeah.
It makes this problem that seems like it would just be trial and error. It seems very elegant.
Yeah, it definitely brings a level of rigor to it.
Yeah, and it's crazy to think this problem has been around for centuries.
I know Professor Uhara, one of the researchers on this team,
Right.
highlighted how, dissection problems like this have been around since humans first started working with animal hides for clothing.
Oh, wow. So this isn't just some random math puzzle. This is connected to a very practical human need
Absolutely.
to optimize the use of materials.
And that connection continues today
Right.
in fields like manufacturing and design, where, optimizing the use of materials is crucial for efficiency and sustainability.
It's a good point. It's a reminder that math isn't just this theoretical thing.
Yeah,
It has real-world applications,
absolutely.
even in something like just cutting shapes.
Yeah, and this research shows how even ancient problems can still give us new insights and tools that are relevant today.
It's amazing to me. We started with this simple question. How many pieces to turn a triangle into a square?
Right.
And we went from basic geometry to these really complex proofs,
Yeah.
and then connected it all the way back to ancient practices and modern applications.
Yeah. It really shows how math is all connected, doesn't it?
Yeah, absolutely. And now we know for sure 4 pieces is the minimum.
Yeah.
It's settled, but it makes me think, what about other shapes?
Right.
What if we go beyond the triangle and square? Are there other optimal solutions waiting out there?
I'm sure mathematicians are already thinking about that.
Yeah.
Like how many pieces to turn a pentagon into a hexagon.
Right.
Or a circle into a star. These problems can get really complex really fast.
I bet those simple shapes we learned about in grade school are suddenly
Yeah.
full of possibilities.
It is kind of mind-blowing. And that's one of the things that makes math so interesting.
Yeah.
There's always something else to look at, another puzzle to solve. Who knows what connections and applications we might find, as we keep looking into these geometric mysteries.
I'm excited to see what other old math debates get settled next.
Me too.
It's been fun talking about this with you.
Likewise.
And to our listeners out there, we leave you with this: keep your minds curious and your imaginations going. Maybe you'll be the one to solve the next big shape-shifting puzzle. Until next